That's all the French I know, I'm sorry. This was originally going to be a joint talk between myself and Alex. Alex couldn't make it, so you get me. And it's because of that we're like going to kind of focus on the researchy bit and maybe less on the production bit, but I'll try and say a little bit of both. So to get started, if this works, there we go. So we have the kind of standard intro stuff. So it turns out we have all these nice graphics and stuff that we're supposed to use for official presentations. I couldn't find them. So eBay, you've probably heard. Who's not heard of eBay? Yeah, okay. We do a lot of stuff. It's big. The kind of relevant info for this one is, let's say on our US site, at any given time, we have something like 800 million items. And for the most part, we don't know what those items are. So the talk's going to be a little bit about that. And what I want to do is kind of tell you a story about the problem, a little bit about the way we solved it. I'll go into some specifics, and then I'll go even past that into some stuff that Alex would normally talk about on how we actually then took that into production. So about me. So I came from math. I did a couple of postdocs at MSRI and one in Reykjavik. I started in eBay at Search. Now I run a small data science team in a group at eBay that sits between eBay and PayPal, which is a kind of an interesting place to be right now. So next year I'm sure I'll have something even more exciting. If you want to email me or yell at me on Twitter, there's my Twitter thing. Okay, so research. There's a kind of a nice quote from one of my colleagues, which is, you sit down and you sort of ask yourself this question, do I know what I'm doing? If the answer is yes, you're probably doing engineering. And if the answer is no, you're doing research. So this is kind of in the research camp today. So here's the basic problem that I want to talk to you about. So eBay, we have a lot of items, say 800 million, let's start with on any given day. We have catalogs, but the catalogs cover a tiny bit of the site, like maybe 30% if we're lucky, but probably more like 10 to 15%. So if you're somewhere like Amazon or Walmart or something like that, you tend to have a pretty fixed catalog. eBay, you can sell anything you want, right? And for reference, like if I wanted to go and sell this shirt, which is from like an eBay hackathon, like I can list it on eBay and say I'm selling a black shirt, and we take it, right? You could also say you're selling, this iPod and give me the serial number, which is great, and we know exactly what that is. But you might also tell me you're selling a black shirt, and we let you do that too. So our job is to kind of make some sense out of that stuff. So even if we can't identify exactly what you're selling, maybe we could at least put it into a bucket with a bunch of other stuff that's like it, right? And look at stuff that we've sold historically that's also like that, right? And sort of make some sense out of it. So the things that we want to make sense out of is how much does it cost to ship this, right? What should I do with this when it hits search, right? How do I sell you things that are similar to this, right? So it's kind of your standard commerce problems. It just turns out that we don't have fixed targets. The other fun thing about our items is that we turn over like 15% of them per day. So anything that you're learning against in your standard sort of machine learning approaches is also transient. So if you can nail down kind of what these guys are at some rough level, it also makes that a lot more fun. Also, if you have questions, stop me at any time. Okay, so of course you all know how to solve this problem. It's through clustering, right? And then you come and you sit down, and you say, well, I want to cluster some stuff, and there's some standard ways to do this, right? There's all these, k-means and hierarchical clustering algorithms. But then you kind of scratch your head and go, well, like, how many garden gnomes should there be, right? I don't know, right? How many black shirts are there? How many, so I was doing this on the UK side, like how many cricket bat mallet, I think. Anybody know what a cricket bat mallet is? Yeah, like one of you. So I know what that is now too, which is kind of strange. But so at the end of the day, we don't really have a handle on how many of clusters there should be. So maybe a better way to do this is to basically, going back to this picture, to build a big graph right? And I just want to put edges between things that are similar for some version of similar. And then maybe I can look at the connected components and that would give me a cluster, right? Or maybe if I don't even need to know the entire cluster, I can just use that similarity to give me, you know, the 5 nearest things if I'm merchandising. So this is, again, an eBay item. If you've never seen one, they kind of look like this. So we have a bunch of stuff kind of coming in to represent an item. So the stuff I'm going to talk about here is really kind of title-based. Most of our stuff works off titles. Sellers tend to put the most interesting stuff in the titles rather than the descriptions. Descriptions are pretty noisy. Images is another interesting one. You know, down here we have like images. We also have stuff like user behavior, which is actually really exciting, but I'm not going to talk too much about that. So if I'm going to look at a title, you know, there's stuff in here. I've got standard sort of tokens. I've got diagrams. I've got like unit of measure. You know, this is a 50 horsepower motor. I've got token and position information, like, you know, this was the first token, this was the second token. That sort of stuff becomes interesting for us. And of course, you know, you go and you do the standard stuff of you take out, you know, stop words and you look for synonyms and et cetera, et cetera. So as an example, you know, here's some features we might pull out. So you might say, you know, okay, there's a token Fairchild, you know, and there's a sleeve French and Blue Life. Sellers actually come and tag stuff for us sometimes if we're really lucky. You know, they tell us the brand or country of manufacturer. Otherwise, we might actually go through and try and do some like name entity recognition and figure out that this thing's actually an engine or the brand is Kohler. So as an example, here's, you know, how we might decompose a title. So here's the title up here, right, and the colors kind of correspond to the features that we ripped out in the bottom. So from this, you know, we have stuff like the token names, but then we might pick up like a bigram, hot pink, and then we might look at things like, you know, in position 0 we had something like hot, and in position 1 we had pink. You know, down here they might have told us that it's a fitted case skin and it's made of rigid plastic, and so on and so forth. So pretty standard stuff. The problem with this is now you have to make a new dictionary, right? So I want to basically look at all these different features, and I'm going to make a vector. But what that really means is I kind of need to assign a number to every place in this massive vector. So sparse vectors, luckily, we know how to deal with these. It's not so bad. We can store them as, you know, a hash map or something like that. But I need to at least go through so that when I tell you that I have something in position, you know, 113,061, that it means the same thing every single time. So this is also a bit annoying. And, you know, at the end of the day, you get things that look like this. But, you know, this goes out to a couple million instead of, you know, at the end of the page here. And probably instead of ones, maybe we've gone through and done some sort of like inverse document frequency type things to assign things. So back to the basic idea. So you look at your, you know, your clusters, you look at your graph. Everybody who's connected up to them, we call that guy a cluster. And the kind of, you know, what we're going for is something like a cluster to us is basically a product. It may not be a product in the sense of I could swap it out for you at buying time and you would be happy, but it's a product for us in the sense that maybe if I know about a product for the search engine, right, and I see something brand new and I can map it into this cluster, then it's good enough. Okay. So here's an example, like one of the first ones that we looked at. So it's probably really hard to see the features, I'm sorry. But, you know, so it turns out we have Lego programmers, right? So I go into the Legos category and I see programmers. And here's, you know, the stuff that was interesting about it, right? There's, you know, programmers, computer, Lego, Series 7, 8831 must be like the part number or something. Minifig, you know, we have Lego red flowers. Then we move on and, you know, we looked at like wigs. And, you know, we're doing pretty good here. So it turns out all this stuff, the Legos and the wigs and things you see here, was actually one of the research scientists that was listed at the beginning of the week. She was basically doing this on a kind of reasonably beefy machine with like MATLAB, and she was sampling, you know, a few tens or hundreds of thousands of things out and kind of running this stuff on it. And it was doing pretty well. And then we got here. So records and albums. We have a category for records and albums. There are a lot of records albums. Like, there are a lot of distinct records in albums, like way more than if you were to go and sample out a few thousand things. Like, you're not even starting to scratch the surface of the number of records and albums we have, right? Because we have just, we have records that were published, but then we have ones that were, one-offs from specific events, and we have, the, I don't know, the French version of this particular English album, and so on and so forth. So it became pretty nasty, and we realized at that point that there's no possible way this is going to work off of just sampling. So we really need to look at everything. If you were an executive, then this would say big data, but I like you guys better than that, so it just says scaling up. The problem is, if I want to build this graph, let's say I have 10 million items, right? Now I've got something like 10 to the 16th comparisons I need to do. We've got a pretty big Hadoop cluster, but we're not going to do 10 to the 16th. So, it turns out that we basically at this point had to turn to some fancy math. So really quick, just kind of here's where we are. So we basically start with kind of raw item data, which I'm kind of glossing over. It's actually stored in a lot of different places, so we have to join all this stuff together. So we start with our items, we then turn it into vectors, and then we're going to essentially do something called min-hashing to at least get things that are similar into buckets so we can do real comparisons on them. So min-hashing. So who's heard of this? Oh, that's good. Okay. So I'm not going to give you an in-depth explanation of min-hashing, but so here's the kind of intuitive view. I take a set, I can essentially generate a whole bunch of numbers that describe that set. So, and it turns out then that the probability that two sets end up generating the same number approaches their Zhicharevich similarity, which is a nice set similarity measure, as you blah, 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 off to infinity and take limits and whatnot. But the good part is that it's a really nice way to sort of get things that are probably the same together without doing all the comparisons that you would normally have to do. So, as a concrete example, I've got basically like some Miles Davis records right over here, and they basically land in this bucket, and then there's some John Coltrane stuff over here, they land in this bucket. Then maybe I've got this one that defies categorization from what we knew before, and it's got Miles Davis and John Coltrane, right? So it lands in both buckets. So the important thing to note here isn't that these buckets are going to be the products. The buckets are essentially a way for us to take this massive n-squared problem and turn it into a lot of small n-squared problems. And it turns out that this is what MapReduce is really good at, right? I can compute n-squared in a lot of small buckets really easily. Computing n-squared in a giant thing is essentially impossible for us. So I go through, I do all this stuff, and then I do the expensive comparison in the bucket itself, and I just put out the ones that were actually past the similarity threshold, right? So at that point, I've got my graph. But my graph is written down as a series of edges instead of something a little bit more useful. So, if you're following along at home, we did the min-hash, and now we actually need to find connected components. So it turns out that, we were doing this a little over a year ago. So Spark was pretty exciting for us at that point. We don't have at eBay a big Mesos cluster, so we were running this on Yarn, right when Spark on Yarn came out. We'll talk a little bit about that later. But if you haven't seen Spark, it's sort of like MapReduce, but we don't need to communicate via disk, and we don't need to pay this nasty overhead cost of setting up jobs every time I want to change from a reduced phase to a map phase. And so what the kind of, at the end of the day, the nice thing is, this connected component algorithm we want to do is kind of expanding search. It's an iterative algorithm. It's terrible in sort of basic MapReduce. It works great in something like Spark, and we're looking at a difference of milliseconds versus tens of minutes per iteration. So, it would take me days to do it with regular MapReduce, and it takes me a matter of 10 minutes to do it with Spark. So, idea, you take your buckets, or you take your edges, you find the connected components, and then you output the function. Okay? So, and this is kind of what they look like. Let me see. Here we go. So these are, again, a little bit hard to see, but like this guy says, you know, New York Yankees iPhone 5 hard plastic case for shipping, and this one says New York Yankees Stadium iPhone hard case cover snap-on, and this one says New York Yankees logo iPhone 5 hard case cell phone. You know, and so this is maybe a cluster that we found in here. There's another one down here which is around Blue Jays. Turns out, you know, we have hundreds of thousands of these things that pop out. Some of them are a little bit too big, some of them are a little bit too small. This is all kind of tunable, right? You can even look inside a cluster, you know, in Spark and say, you know, is this cluster too big? Yes. Okay, then sort of start stepping up the threshold of stuff that I want to split on until I get something close to reasonable. So that's the basic story. And you're asking at this point, aside from the fact that you mentioned Spark, what does this have to do with Scala? So I can actually get into a little bit more about that. So what we use to actually to do most of the heavy lifting here is actually Scalding and not Spark. So Scalding has a really cool logo, finally. It comes out of Twitter. I probably should have put that on here, sorry. So the sort of great thing here is that I can write what looks like pretty close to idiomatic Scala collections code, and just through some magic, it turns out to become MapReduce jobs. This is pretty awesome, right? I don't know if who's ever written like standard Java MapReduce stuff? Yeah. And then who's written like Pig or Hive? Yeah. So here's the problem. If you're not in the group of people that raised your hand for one of those, I can write Java MapReduce stuff, but I don't hate myself, and I don't hate the people that read it. So to do something really simple, like I'm going to show you, right? I don't want 18 different classes and a bunch of abstract constructor being factories or whatever the hell that has to go with this. Similarly, I could probably do the same thing like Pig or Hive, but I really, really don't like 6 hours down the line when I essentially have a mismatch in types and the whole thing barfs, right? And I just lost 6 hours and however much computation that was. So there's this fantastic sort of middle ground where I get my types and I get conciseness and expressiveness and all this other stuff. So Scalding is where it's at, I think, right now. So the idea here is I write what looks like pretty much Scala code that I would have written on lists or something like that in memory. I hand it to the planner, and Scalding, it figures out how to rewrite it as MapReduce jobs, and then it makes this big directed acyclic graph, and it goes off and does it. The nice thing is when things get a little bit more advanced and we're running on something like Spark or Tez, Scalding can actually just swap out the bottom, and you don't care. You're just writing the same stuff and getting a huge speed up for free. I think it has a fantastic community. I think it has really good documentation. You'll see a counterpoint to that later. But it's also got all your favorite, functional built-in stuff like semigroups and monoids and rings and etc. So here's an example. I think that's legible. So this is kind of raw stuff that I just ripped right out of some code that we were using. When I came in to work with this other team on this project, they'd really never written any Scala before, so I kind of coached them through writing this stuff, and this is what the end results look like. So, maybe it's not perfect, but it actually worked out pretty well. And at the end of this kind of, I forget how long I was there, 12 weeks or something, they were actually pretty productive in Scala stuff, so it was actually a nice motivator as well. So even if you've never written any Scalding or MapReduce or anything like that, you can probably infer what's going on. So I kind of skipped over the part where I got these rich item things. But basically so now this is actually the Scalding bit, as I'm calling flat map, right? I handed a function, anonymous function even. Basically I take an item, and I have a bunch of feature extractor functions, right? And I basically just do a fold on that. I walk through and apply the function, each one of these, and I keep increasing the set of features that I want. And then I basically spit out, the feature I spit out in ID and the feature set. So what I'm really doing here is building towards this sort of what's called inverse document frequency calculation. So I can take that guy, right? Swap this is just a sugar method for if I know I have a tuple of arity 2 coming in, I can swap the features around. Group is another sort of sugar function installing, which says do a group by on the first field of a tuple. and then size, which I'll tell you about in a second, is kind of neat. So at the end of this, I basically get, right, for every feature, I get a count of how many documents it appeared, right? So, and then down here, I can take the exact same thing that I had started with up here, and I can basically just get the actual size for it. So how many documents did I have overall? So a document in this case is an item, sorry. And then, you know, I can keep going. I can take my sort of features with their counts. I can sort of join it up with this actual single number. And then I can just actually do the IDF, the inverse document calculation, which is this guy. It's just the log of essentially the number of items divided by the number of times I saw this feature. It's a kind of standard thing. You can look it up on Wikipedia. The nice thing is, like, what this actually turns into at the end of the day is like 7 MapReduce, right? And it's not even just a path. It's, you know, a kind of complicated graph that, you know, goes and computes this bit, and then you forks it and uses these 2 things, and so on and so forth. I don't care. I just wrote this code here, and it does it for me. It's like magic. So here's kind of what's going on. So I want to say a little bit about Algebird. So Algebird is kind of came along, I guess, a little bit after Scala Z or Scala Z, if I'm on the side of the Atlantic. It's kind of a lightweight version of some of the nice stuff out of Scala Z. So they, you know, have built-in monoids and semigroups and monads and stuff like that. Algebird, though, is kind of, it got ripped out of Scalding at some point to be its own standalone thing, but it's really kind of baked into Scalding at the core, and this is kind of an example of that. So when I called size, and this is actually just ripped right out, pulled out of the actual Scalding source. When I called size, what it really did is it called map values, which works exactly the way you'd expect it to. Basically, it sends everybody to one long, and then calls sum. Okay, great. So what the hell is sum doing? Well, sum actually has an implicit semigroup, and so it knows about, Algebird has kind of semigroups already defined for most of the stuff that you care about. So it calls sum left on that, and then so on, and actually you can see down here, okay, what's really happening is we're calling the semigroup sum option and getting an iterator and spitting that out as map value string. So this is all kind of sugar that's done for you, but the nice thing is that for like 99% of the cases, calling something like sum or size or something like that really kind of just does what you expect it to do, which is saves you a lot of time. If you really desperately, you know, need your own like hipster monoid or whatever, you can go in and define your own hipster monoid and add a hipster class or whatever. So it's a massive, massive time saver. The other thing that I really like about Algebird is it actually gives you a lot of nice stuff out of the box that you would want, like Bloom filters. So here's another example. It turns out when we're sort of getting these items together, right, the data for our items are stored in like multiple places across our Hadoop cluster. And so actually I need to do some massive joins to get all these guys together. I can speed that up a lot using something like a Bloom filter. Who knows what a Bloom filter is? Okay, that's better. So if you don't, think of it as a probabilistic set, right? So I can basically take an item or an ID and ask the Bloom filter, have you seen this before, right? And if the Bloom filter hasn't seen it, then it's guaranteed to tell me no, right? If it has seen it, right, then it might still tell me no. I might read it backwards. No, excuse me. Is it the other way around? Sorry. So if I haven't, I'm guaranteed if something's not in the Bloom filter that I haven't seen it before, right? Because otherwise I would have flipped that bit. If I tell you it's in the Bloom filter, there's some small probability that I actually hadn't seen that thing. It just turns out there was a hash collision. So think of it as like a big bit vector, and I sort of turn on, you know, the bits as I hash stuff in. So what it means, though, is that if I have 2 huge things and I do a big filter on one side, right, and I want to join them up, instead of actually running across all of them to join, I can compute a Bloom filter as I'm doing this filter over here, the regular filter, send the Bloom filter over this way, throw out, you know, 99.9% of the stuff that's not actually going to be over here. Then when I do the join, I get a much more efficient join, and it's way faster. So to use it, basically there's a bloom filter monoid, and I basically just, create a small bloom filter for every one, and again, the way plus works in algebra on bloom filters is it just makes you a bigger bloom filter, which is pretty nice. So it turns out they also have stuff built in. I think somebody mentioned it yesterday, like count and sketch, which we ended up using, and min hashing, of course, which we use quite a lot. So any questions so far? Okay, so if Alex was here, this is the part where I would say, okay, this is great, and end the talk. And then Alex is supposed to jump up out of the crowd and say, no, you forgot some stuff. So it turns out that I came in sort of working on this as a research project. Alex is the one that had to take it. Alex and Daniel, who I mentioned at the beginning, sort of had to take this guy into production, and they kind of ran into some issues with that. So I have Alex's thoughts on that, though, which I'm calling notes from production minds. So normally I would have helped out with this a lot more. It turns out I was kind of in a rotational program in the company, so I had to basically bounce every 6 months, and I couldn't stick with them. But in general, we don't just abandon things to people to work on, but in this case we did. So here's some thoughts from Alex, which I thought were kind of interesting. So it turns out when you start these things as research projects, at the end of the day, what you end up with is a huge mess. And try as you might, right, a lot of kind of nice discipline goes out the window because you want to essentially try this next thing and try this next thing and try this next thing and so on and so forth. And so you get this big, massive piece of spaghetti. And we go back through and clean it up every now and then, but it's still not something that I would wish on somebody. So the first thing they did is they really had to kind of basically go through and clean up everything into something that looked like they could maintain it. Also, as I mentioned, the folks doing this is kind of their first taste of Scala. So they get the kind of double learning curve of Scala and Hadoop networking stuff. So I think they did a fantastic job of this, but it was a kind of a long, grueling process for them, I think, and I think they did I think there's a lot of credit for this. I'm just too bad Alex wasn't here. But so kind of here's some things, stuff that you kind of think about. We write tests and stuff like that, but I think at some point we moved so fast that we didn't have tests for certain things that we'd thrown in at the last minute and so on. So they did that. But there's kind of other little things in here, like for us when we're sort of running this as a research project, it's a lot easier to write these kind of individual pieces and kind of cascade them together, through some connector. In fact, we use this thing called Luigi, which is pretty cool. It came out of Spotify. It turns out that for them, this is a lot harder to maintain, right? Because you have all these different moving pieces. So I think one of the first things they did is they went through and kind of unified this guy. Same thing, right? It turns out that they had different end goals at the end than we had for our research project. So they went through and they wanted to be able to sort of use this as a skeleton, right? And then have different end targets. So a lot of that was basically using this sort of inheritance stuff. So this is actually something where scalding, being pretty much basically just Scala, gives you a huge advantage over stuff like Pig and Hive, right? I actually can use the sort of nice object-oriented stuff and have sort of these base jobs and inherit from them and get everything I need, and then just make little tweaks to it as I go. So the next place where we had a lot of trouble, and I helped them with this quite a bit, was scaling. So when I was running this, Gillian and I, we were dealing with what we call sort of leaf categories, which we have like 15,000 of, and then we sort of started moving up to meta categories, which we have, 10 or 20 of. So a meta category is like quite a few leaf categories, sometimes a couple hundred. Some of them, they were great, but it turns out, when they were running this for reals, they started bumping into some real problems. So, this is like a big deal, right? So now my dictionary can grow to be so big that really it's becoming difficult for me to hold it in memory, right? And so this is on a standard Hadoop cluster where you get a couple gigs a heap at the most. One of the ways that we've actually started to go around this is to basically stop using a fixed dictionary and use like a count and sketch. So if you remember your bloom filter, take this bit array and make it a 2D array now. And the count and sketch tells me something about roughly how many times have I seen this thing rather than have I seen it or not. If I know roughly how many times I've seen it, then it's easy for me to do this like idea of calculation on the fly within some probability bound that I probably don't mind. I don't know that they ever got to that bit, but it's one way to solve this. The other thing is just kind of standard, shared environment stuff, right? When we were doing a lot of this sort of development work, we were on kind of our almost own clean, smaller but clean Hadoop cluster. When they want to turn it into production stuff, now they have to fight for resources with everybody else. So the first thing they did is they said, okay, well, we can run all these 20 meta categories. And I think they basically choked up the whole cluster, and then, people get on the phone and start yelling at them, and it basically didn't work super well. So, one thing you can do, of course, is they, in their refactoring process, they figured, okay, it turns out we can go through and do a lot of stuff like the common things like computing dictionaries, doing the joins ahead of time, and then basically Scalding has this nice fork, which essentially guarantees like a new computation to run. So you can essentially keep everything as kind of one big pipe for a long time, and then fork it into all these smaller ones on a per category basis. And that tends to not choke the cluster as much because all the heavy lifting was done at the beginning. So graph processing. We had a terrible time with Spark. So this is a year ago. This is like Spark 0.8.9. This is Spark on Yarn, which I think makes a huge, huge difference. We weren't running Spark on Mesos. And in my experience, the biggest problem we have with Spark on Yarn is that there's no way to get back resources, right? So basically, I tell you the chunk of resources I need, and those are mine forever, right? So now I have sort of a dilemma. And in fact, we rewrote this whole job to run in Spark, even the stalling bits, and it was even worse than just the simple parts. Because the problem is we start with this massive set of stuff, right? And then I kind of have a funnel, right? And I kind of funnel stuff down, I filter, I join, I aggregate, and now I've got this much smaller set of stuff. And it's not it's not a tiny amount of stuff, but it's way, way smaller than what I started with. So what I started with might be on the order of, probably dozens to hundreds of terabytes, and what I end up with at the end is, on the order of tens to hundreds of gigabytes. So it turns out that, I have to make a choice now with Yarn and Spark, is do I essentially want to choke at the beginning, right? So I can start with a fairly small resource pool and choke it for a long time and hope it pushes through into the other phases and then it will run nicely, right? Or do I want to basically get all the resources to start with, right, and sort of block everybody else out of the cluster, right? And even worse, now when I get down to this bit where I want to do this iteration, if I have way too many nodes, I end up having a lot of network congestion because everybody's sending stuff instead of most of the processing being happening on a given node. So this bit us a lot. We tried Giraffe. We tried multiple versions of Giraffe. It worked a little better in some cases, but the problem is that in my opinion, it's way, way harder to be expressive in Giraffe than it was in Spark. So in Spark, I could spit out pretty much anything I like. Like, if I went way back here to these guys, to hand it to people who know about specific categories, we'd actually just write out HTML. Like, this is the output from Spark. It was literally HTML. From Giraffe to get it to do something like HTML versus, the formats that other people are going to want. We need brand new abstracting constructor factories or whatever to do that, and it's, it's a lot of work. So certainly it was not fun. So they kept pushing this stuff. Spark, of course, got way better. Our admin guys started catching up. Our ops guys started catching up. So I think at the moment we can do this now with, I think that's should be 300 million vertices instead of edges. So 300 million vertices is like a meta category or two over an entire year of history. So actually, we're getting better at it, but it was a kind of a long, painful process and a learning process for everybody involved. Both on the sort of development side and the operation side. I think they got to be like, either really good friends or really good enemies with most of our operations guys. So it turns out actually, when they sat down, they started thinking about like, well, what are we actually trying to solve here? And a lot of times we're just trying to solve something like, for merchandising, can you tell me, somebody comes in off an external search into eBay and lands on an item, that item's gone, right? It got sold 5 minutes ago. Can you show me one that's just about the same thing, right? And then you could just buy that one instead. It turns out for that one, I don't need the entire connected component. I only need like 5 things that are pretty much the same, right? So at that point, I could actually just go straight from the sort of min hash buckets, right? And just spit out the 5 most similar things, right? And then we collect all those guys up. And actually, this is kind of a nice comment here. This is when they really started. I think monoids started to click for them, right? Because there's this nice top K monoid, right? And if I add 2 top K monoids, I still end up with the top K things. So out of every bucket, they would put out the top K for a given item, right? And when you aggregate that now, you still end up with the top K for a given item at the very end, even though from multiple buckets you're getting better things. So I think at that point they're like, oh yeah, this is really good stuff. It turns out that maybe we were solving a problem that we didn't need to solve in some cases. For other cases, I think we're still sort of punching at it because we, I don't know, maybe it's pride or something, but we really did want to solve these. So, and then kind of, there's a couple other things for the similarity stuff. It turns out that the items themselves, right, when you hash them, it's not quite as uniform as you wanted, right, the feature sets. And it turns out there are a lot of items, which is just crazy. I mean, this is, you have 800 million things. We have a few million items on the site where the title is nothing but punctuation, right? It's just one of those things where you let people or APIs or something, list items and you get junk sometimes. So I think what this came down to is we realized that, there were a couple sets that were occurring more and more, right? And so essentially we were overloading certain buckets quite a bit. And we would go to a bucket and it would have, basically like over 30,000 items. And that starts to be a kind of an issue for our n-squared comparisons now. Like it's doable if you let it sit for a long time, but we don't really want it to sit for a long time. And it's probably a symptom of something else. So it turns out the Twitter guys who wrote Algebird were pretty sharp. They put in a lot of nice things you could tune here, in terms of bucket size parameters and all this stuff. So you can make a lot of trade-offs. We played with this stuff a lot. We tried, essentially min-hashing again inside big buckets and stuff like that. I think at the end of the day, actually what we ended up doing is just throwing away the big buckets. It turns out it didn't really hurt us at all, and they were probably things where essentially the set was empty or had like one thing in it. That's kind of, but this is all kind of painful lessons that we learned along the way. If you're doing this, I would highly recommend early on in the game looking at what your distribution of buckets looks like and figure out why some of them are getting hit way more than others. And I think kind of the last thing, so this is actually just straight from Alex, which was nice. They came from like 0 Scala to up to their necks and all this stuff. I think he had a great time with Scalding. And then like I said, they started to realize that hey, having a lot of this stuff baked in, like monoids and things like that, you're basically getting their semigroups. You're getting the advantages of them without even worrying about them at first, right? And then when you get a little bit more adventurous, you can sort of push and go like, hey, maybe I should add things this way instead of this other way, and now you're making your own monoids, which I think as you're learning this stuff is really a fantastic way to do it. So one real issue though is that for the most part in the Hadoop ecosystem, like these aren't the standard tools people are using outside of maybe a couple places, right? This bit here about the sort of debugging and logging, the Hadoop is still this kind of fragile, distributed system, and having our operations guys, when they go and flood the cluster and choke it, the operations guys come back yelling at them, and they don't realize what's going on. When their jobs don't work, right, they basically take their logs and go to operations and say, hey, what the hell's going on? And the operation says, well, I don't know, like what's a Scala? So, it sort of took a while for them to start speaking the same language, I think. This was definitely a non-technical issue, more of a people issue, just for them to be able to do this. And sort of, I think I underestimate, I've been involved with stalling and cascading for a long time. I'm reasonably good at reading error messages from these guys and figuring out, if it's my fault or if it's something going wrong with our Hadoop cluster. when you're new at this, you have no idea, right? And it's, there's so many horrible things that can happen, from serialization errors to, opening too many file errors and crap like this. And it's a really nasty sort of place to wade into. And I think probably, we could do better at helping with that, I think. But so that's kind of an interesting thing. So like here's my, Alex's take on this is, scalding documentation is, I think actually that their code is really simple, and that's what I mean by their documentation is really good. I can sort of hop into any scalding function and know what it's doing, sort of by looking at it. Turns out if you're if you're brand new to Scala or scalding, that's a little harder than I expected it to be. So this is a kind of a takeaway. That again, it's not like Pig or Hive or regular Java MapReduce. So it took a little bit to sort of get into understanding what's going on or what's available to you even, right? Like maybe you don't know that there's something called a sketch map, which will actually go through and basically make the sort of count and sketch stuff for you already. That's all ready to do something else with. Or maybe you don't know that there's an approximate count function which uses a hyperlog structure instead of doing a raw count, and it's super fast and uses no memory. This is stuff that's great, but maybe it needs to be exposed a little bit more. Okay, so then understanding stuff like Spark, like I said, in 0.9 we ran into a lot of trouble. It's called 0.9, so what do you expect? But I think that most of my experience with Spark so far has been that it's a really great idea, and then when you go to use it, if you're not using the sort of standard Mesos cluster, you run into problems. I think that's changing super fast. The Databricks guys are really smart. They know this is a problem. They're working on it hard. There's Cloudera guys working on it too. But I think it's definitely something to worry about. And this was kind of underlies, I think, most of the Spark issues here, is that when you're running in a shared environment, memory is a premium, right? So, we have a Hadoop cluster, and I don't know, it's up to like, we have a few of them. I think each one's like 2,000 nodes or something, and each machine has, I don't know, 100 gig of RAM. But it turns out, when you have hundreds of people running jobs at the same time, that's not as much as you'd expect. In fact, there's this kind of one of my favorite sort of quotes I had was from Josh Willis, who's a guy at Cloudera, and he was at Google for a while. And he said when you go to Google, you're a new engineer, and they basically you get to run on their distributed systems, and they go, you get a terabyte of RAM, right? You go, wow, I get a terabyte of RAM, like, oh my gosh, that's amazing. He's like, well, guess what fits in a terabyte of RAM at Google? Well, not even like one integer column for a day of logs. So, this is kind of the same issue we bumped into. Like, like a terabyte of RAM. You're like, oh shit, that's not a lot. So this is kind of an issue. I don't know how to solve this one, but it's something we definitely ran into a lot. Anyway, so why don't I finish up there? If you have any questions, I'd be happy to answer them if I have a couple minutes. Otherwise, hit me up on Twitter, hit me up email, or just grab me afterwards. So thank you.
Question? Yes, I might have one. Can you go back to your graph processing with Spark slide, for example?
Sorry, graphics.
Yeah, your graph processing problem with Spark, for example. You moved to speak with Zhicharevich, right?
Yeah, so and in fact, actually, I started with Bagel, which is like the Spark Cradle implementation, because actually GraphX wasn't working. Like I had a bug open with them. I think they fixed it, and I think Alex and Daniel ended up using GraphX because at the end of the day, it was still way nicer to use than Giraffe.
So your main problems with Spark were mostly actually about the memory consumption and operational problems. Actually.
Yeah. It's really kind of like trying to fit Spark into our production Hadoop environment instead of having, the standard MapReduce problem, right? You run on this, you run 1,000 nodes that have like a gig of RAM each, right? And it's fantastic. And a lot of the things you want to do with Spark, you're much better off running like 10 nodes with 100 gigs of RAM each. The operations guys don't necessarily see it that way, so we're, kind of in this constant push and pull with them to free up resources or let us run on those types of resources. I think at the end of the day, what we'll end up doing is probably having a separate cluster to run Spark stuff on. Maybe this Nantro Mesos instead.
Okay, right, thank you.
I have two questions. The first one is about I'm a little lost when you talked about the connected components. Can you explain why
why we want connected components, or how to find them?
Why do you want?
Oh, sure. So remember, what we're doing what's coming out of these min hash buckets is a pair of items, which we're calling an edge in the graph, right? So, but it turns out it's possible for min hash that maybe there are two items that are really similar that never ended up in the same bucket, right? It's a probabilistic process. So what I really want to find then is all the items that are connected by, right, some common path or some path. So a connected component in the graph. That one will probably give me a set of stuff that's mostly similar, even if they didn't end up in the same min hash buckets.
What are the edges?
The edges? So I put an edge, sorry, I probably should have explained that better. I put an edge between two nodes if their vectors are very similar, right? For some definition of very similar. For us, like maybe, their cosine similarity is like above 0.95 or something like that. But that's something we can play with as well.
Okay. And the second one is about the LSH. Do you implement yourself or do you?
No, so this is the min hash stuff. So it turns out that, again, like this is just right off the shelf out of algebra. They have a min hash monoid, which is fantastic, and we just use that. They actually have some newer stuff that they put out in the last few months, I think, where they have this, there's kind of a newer versions of this min hash process. One's called like dim sum, and one's called disco, where you basically can have like this dimension independent similarity calculation. So min hash is approximating Zhicharevich similarity. Disco can do pretty much anything. In our case, it didn't really matter that much. In fact, I started using like Kanemoto distance or something because the cosine similarity really didn't matter.
Someone else?
Good.
Yeah.
Yeah. Are you doing some image recognition during the vector operation?
Yeah, so the nice thing about also making this graph is that you can have edges from just about anything you want. So we definitely are in the process of trying with images. One of the ones that's actually given us a lot of sort of thing is behavior. So, when in a given session, like a search session, a user clicked on this item and they clicked on this other item, right? If I see that enough, I start to learn that probably these two items are the same. The other nice thing about behavior, sorry, I completely changed your question, I apologize, but the fun thing I really liked about behavior was, a lot of times in the office, we have arguments over, what sort of means, what's similar, right? Like if I have, cell phone cases and one of them is red and the other one is blue, but they're the same model of case, like are those similar, right? Should I consider those in the same bucket? And this changes, right? It changes for clothes, it changes for, iPods, it changes for iPhones, it changes for phone covers and cricket bat mallets and all this stuff. So it turns out when you use behavioral features, the users actually tell you, right, for the most part. If people click on the red one and the blue one together a lot, then it's probably the case that they're mostly interchangeable. If they never click on them together, then color is probably a very important thing to this type of product. So we started sort of overlaying behavioral data to get that on them. Okay. Thanks again.
Thanks.